Hello dear students, this is Dr. C. Ashok Kumar. Today we are going to discuss second year UG second year third semester mathematics paper, that is real number systems. Under this we will discuss real number system and completeness, and by using, after listening these topics, we are able to know what is the meaning of ordered field, least upper bound, greatest lower bound, and we are able to know completeness axioms, dead-kind properties, and establishment of their equivalences. Okay, let me start. Before going to start the basics assumptions, first we have to learn what is the meaning of ordered field. In real number system, we are using majorly two binary operations. One is addition and one is multiplication. With respect to these two operations, let me discuss certain properties. First, coming to the with respect to addition, what is the commutative property? If a comma b belongs to R and a plus b is equal to b plus a, then we can say it is commutative property. Coming to the associative property, a plus b of plus c equal to a plus of b plus c for all a comma b comma c belongs to R. Now coming to the next identity property, if there exists an element 0 belongs to R is such that a plus 0 equal to 0 plus a equal to, again it is equal to a for all a in R, then we can say here 0 is the additive identity in R. And coming to the next inverse property, let us suppose a belongs to R, then there exists minus a is also belongs to in R is such that a plus of minus a equal to 0 or which is equal to minus a plus a, then here minus a is known as the additive inverse element of a with respect to addition in real number system. Okay. Next, coming to the same properties with respect to multiplication. Coming to the commutative property, a comma b belongs to R, it implies a dot b equal to b dot a for all values of a comma b. If this condition is true, then we can say R is satisfies commutative property with respect to multiplication. Next, coming to the associative property with respect to multiplication, a dot b dot c equal to a dot of b dot c for all a b c belongs to R, then we can say here R real number system satisfies the associative property with respect to multiplication. Similarly, coming to the identity property, there exists 1 belongs to R is such that a dot 1 equal to a equal to 1 dot a for all a belongs to R, then we can say here 1 is the multiplicative identity element in real number system. Similarly, coming to the inverse property, suppose if for a not equal to 0, then there exists a inverse belongs to R is such that a into a inverse equal to 1, it is equal to a inverse into a. Then here a inverse or 1 by a is called the inverse element of a with respect to multiplication in real number system. Similarly, coming to the distributive properties. In distributive properties, simultaneously I am going to use both operations as multiplication as well as addition. So, coming to the first distributive property, a dot b plus c equal to a dot b plus a dot c for all a, b, c belongs to R. This is a distributive property, and apart from these we have some more properties. Let me discuss one by one. If a not equal to 0, it implies a inverse also not equal to 0, then a b equal to a, it implies b equal to 1. That is, by consolation law I am writing a b equal to a, means if you cancel a on left side on both sides, then b will goes to 1. Similarly, we have one more consolation law, right consolation law, b into a equal to a, if you cancel a right side, then b equal to 1. So, these two are the consolation laws, left consolation law, right consolation law. Similarly, minus 1 into a equal to minus a, and these are the general properties. A into b equal to 1, it implies a equal to b inverse whenever b not equal to 0, and a inverse whole inverse is always equal to a. Similarly, you have certain general properties, and I will discuss one more important property here. If a dot b not equal to 0, it implies either a not equal to 0 or b not equal to 0. Then the two real number system A and B, we have either A less than or equal to B. Here less than or equal to is called ordered relation in real number system. Next, coming to the next definition. There is a non-empty set P which is subset of R is called strictly positive real number, then it must be satisfies if A comma B belongs to R, then A plus B belongs to P. If A comma B belongs to P, then A dot B belongs to P. If A belongs to R, then exactly one of the following conditions must be holds, that is either A equal to P or A equal to 0 or minus A equal to P. See here, this third property is known as trichotomy property, and we can define this property in another way also. If I say two elements A comma B belongs to R, then the relationship between these two elements must be either A less than B or A greater than B or A equal to B. This property is known as law of trichotomy. So, this I will explain next slides here. Let A, B, C belongs to R, then if A greater than B and B greater than C, it implies A greater than C. Similarly, A greater than B or A equal to B or A less than B, that is, this is the relationship between any two elements. One of the element must be either A greater than B or one of the element must be less than B, that is A less than B, or the both elements must be equal. This property is known as the law of trichotomy. Similarly, if A greater than B and B greater than A, then implies A equal to B. Next, see here, these are the modulus properties. Mod A equal to 0 if and only if A equal to 0. If mod of minus A equal to A for all A belongs to R. Similarly, mod of A B equal to mod A into mod B for all A comma belongs to R. If C greater than or equal to 0 and mod of A less than or equal to C, if and only if this result must be holds whenever the A must be lies in between minus C to plus C. Similarly, minus of mod A is always less than or equal to A, which is less than or equal to A for all A belongs to R. And coming to the next, one of the most important property, that is triangular inequality. With the help of these inequality, we have certain problems also. First, let me discuss the theorem and its proof, that is triangular inequality. I will read the statements here. First, coming to the what is the statement of triangular inequality. If A comma B belongs to R, then mod of mod A minus mod B is always less than or equal to mod of A plus or minus B, or which is less than or equal to mod A plus mod B. Now, coming to the proof of this. Mod of minus A minus of mod A is less than or equal to A, which is less than or equal to plus A, and similarly minus of mod B is less than or equal to B less than or equal to mod B. Then we can define minus of mod of A plus mod B is always equal to minus of mod A minus of mod B, again which is less than or equal to A plus or minus B, again which is equal to less than or equal to mod A plus mod B. Thus, mod of A plus or minus B is always less than or equal to mod A plus mod B. Similarly, you can come to the next another proof. Mod of A is always equal to, I am writing mod of A equal to mod A minus of mod B plus B. Here I am adding and subtracting B quantity for A. So, A equal to mod of A minus B plus B, which is less than or equal to, if you split the mod, the equality will become inequality. So, mod of A minus B plus B must be less than or equal to mod of A minus B plus mod of B. It means mod of A minus mod of B is always less than or equal to mod of A minus B. Similarly, we can prove that mod of B minus mod of A is always less than or equal to mod of B minus A. It implies mod of A minus B. So, from these two we can write mod of A minus mod of B is always less than or equal to mod of A minus B, right. This is the triangular inequality theorem and its results proof. Okay. Now, coming to the next principle of inductions. As principle of induction says that if P is any real number which and let n be any set of natural numbers, for n belongs to n, let Pn of A be statement which must be satisfies the three conditions. First, it is true for n equal to 1, and let us assume n equal to n, it is true. Then we can prove that it is true for n plus 1 also. If you satisfies any property with these three conditions, for n equal to 1, for n equal to n, then with the help of these two quantities we can say that it is true for n plus 1 also. By these three conclusions we can say the given statement is true for every value of n. Next, coming to the definition of least element, that is, let A be a non-empty subset of a real numbers. A real number A is said to be least element of A if A less than or equal to x for every x belongs to A. Next, well order principle. Well order principle states that every non-empty subset of n has at least one least element. Every non-empty subset of n has a least element. Next, archimedean property, as this is also one of the interesting property and a very important property in our real number system, that is Archimedean property. According to this Archimedean property, it states that if x comma y belongs to Q and x greater than 0, then there is a the natural number n belongs to n is such that nx must be greater than y. So, I will read once again these statements here. If x comma y belongs to Q and x is greater than 0, then there exists a natural number n belongs to n is such that n into x is also greater than y. Of course, the proof is obviously it is we can prove this with the help of assumptions, that is n equal to 1, then n equal to 2, that is if x greater than 1 then n equal to 1, if x equal to y then n equal to 2, let 0 less than x less than y. By taking the assumptions x equal to p by q and y equal to r by s, by taking these two assumptions we can write the result nps greater than or equal to n greater than rq and nps by qs must be greater than rq by qs. It implies np by q greater than r by s, it implies nx is always greater than y. Here p, q, r, s, r belongs to natural numbers. Next, countable and uncountable sets. Now, coming to the next topic, countable sets and uncountable sets. First, before going to start these countable, uncountable sets, first we have to know what is the bijection property, what is the similarity properties, what is the finite set. If you know the idea of these three topics, then this definition will become very easy. So, what I am saying, what is the bijection condition, what is the in functions, how we are going to define the bijection property and how we are going to define the similarities as well as finite sets. With the help of these three concepts, we can discuss the countable and uncountable sets. Let us discuss first bijection. Let A and B be any two non-empty sets. If there exists a bijection from A to B, bijection means it must be satisfies one-to-one property as well as onto property. So, what I am saying, if there exists a bijection from A to B, then A and B are called similar sets, or equally we say A is similar to B. That is, if f is a function which is bijecting from A to B, then we can say A is similar to B. Okay. Next, similarity of sets is equivalence relation on the sets of set. A set A is said to be finite. A set A is said to be finite if it is similar to 1 to n for some fixed natural numbers n belongs to n. Then, with the help of these three, coming to the what is the countable set. A set is said to be countable set if a set capital A is said to be countable set if A is either non-empty set or A is either finite set or A is similar to natural number n. Among these three, if n must be satisfies any one of these three, then we can say that n is or that set A is countable set. What is that three conditions? Either A must be non-empty set, or either A must be finite set, or either A is similar to n. Then the set of natural numbers equivalent to a finite set is said to be countable. If there is a bijection of the set onto n to n itself, then it is always countable set. Suppose if any one of the set are not satisfying this any one of these three conditions, then we can say it is not countable. If it is not countable, means we can say it is uncountable sets. Okay. So, a countable set which is not satisfying the three conditions, any one of the three conditions, then we can say that is uncountable sets. This countable set is also called denumerable set or enumerable set. Next, come to some examples. Suppose n is a natural numbers and I want to say whether it is a countable or not. So, I am taking function f from n to n itself. So, n to n itself means it is bijection satisfying the one-to-one property onto condition. So, f is a function from n to n itself and f n equal to n. Then, if the function is defined like this, I am taking domain from n and codomain is n, then it is always a countable set. Okay. Similarly, next, these are the few examples. If n is a countable, then its subsets 2n is also countable. Next, coming to the theorem 1 theorem. Any subset of n is countable. Suppose n is a natural number set, it is countable, then its subsets are always countable sets. And why? Because the proof is from the subset into non-interesting rows of primes and their multiples, and use diagonal techniques to get 1-to-1 property and onto property subsets into n as the theorem. With the help of this, we can prove the subset of any n is always countable set. And in this here, coming to the few statements, a countable union of countable sets is again a countable. So, if n is a countable set, from that n you can take the subsets and take all the unions of all that subsets, the resultant set also countable set. So, that is the statement of this, a countable union of countable sets is a countable. Next theorem, the set of rational numbers is always countable. Similarly, root 2 is not a rational number, it is an irrational number. So, irrational number is not a countable. So, root 2 is irrational number, therefore, it is not a countable. So, this is the proof for showing the root 2 is irrational number. Next, bounded and unbounded sets. Yes, this is also one of the most important topic in real number system, bounded and unbounded set. So, bounded set means, first let us take one aggregate set, that is a non-empty subset of real numbers is called an aggregate of real numbers or simply an aggregate. So, coming to the first definition of upper bound bounded above, lower bound bounded below. So, let me discuss these 4 definitions one by one. So, first coming to the what is upper bound and what is bounded above. Let us suppose A be the any aggregate if there exists a real number m is such that x less than or equal to m for every x belongs to A. So, what I am saying, let us suppose A be the any aggregate set, that is A aggregate means it must be non-empty set. Let A be the any aggregate set if there exists a real number m is such that x less than or equal to m for every x belongs to A, then m is called upper bound of A and A is called bounded above. See here, listen these 2 words carefully. So, what I am saying, A is aggregate set and I am taking x be the any one of the element from that set, and that x must be not less than or equal to, the x must be less than or equal to m for every x belongs to A. Then if this condition is true, then what I am saying, m is the upper bound and that entire set is the bounded above. Okay? And upper bound of an aggregate is not unique, because if m is an upper bound of an aggregate A and m1 greater than m means there will be one more element which is more than to m. So, that I am saying m is unique, m is not a unique, means the upper bounds are more than 1 in that entire set. So, see what about maximum element in that entire set, that is the upper bound. So, if m1 is greater than m, then here m1 is the upper bound. Okay. Next, coming to the lower bound and bounded below. Let A be an aggregate if there exists a real number m is such that x greater than or equal to small m for every x in A, then here m is called lower bound and the entire set A is called bounded below. Okay. The lower bound of an aggregate is not unique if m is lower bound and m1 less than m. So, there is a one more m which is less than to m. In this case, m1 is the lower bound. So, that is why I am saying lower bound is not unique, right. So, with the help of these 4 definitions, lower bound bounded below, upper bound bounded above, we can define bounded set. Okay. Next definition, an aggregate A is said to be bounded if it is both bounded below as well as bounded above. An aggregate which is not bounded, then it is known as unbounded set. Okay. So, an aggregate is said to be bounded if it consists both bounded below as well as bounded above. If it does not contain bounded below, bounded above, then we can say it is unbounded set. Next definition. Next, coming to the next definition, least upper bound, that is supremum, and greatest lower bound, infimum. Let me discuss one by one. These 2 are also one of the most important in real number system. Coming to the first, LUB, least upper bound. See here, if m is an upper bound of an aggregate A and if a real number less than m is not an upper bound of A, then m is called the least upper bound of A. A least upper bound is also called supremum of A. What is the meaning of this here? I will explain this with one interval. Suppose 2 comma 5, a closed interval 2 comma 5. Let us assume 2 comma 5 is any closed interval. In this, we have to divide these closed interval into some finite subintervals with length, each length is 1 unit. Let us take 2 to 5, I am taking 2 comma 3, one interval, 3 comma 4, another interval, and 4 comma 5, another interval. In each and every subintervals, let us take upper limits 2 to 3. What is upper limit here? 3, upper bound 3. Similarly, 3 to 4, upper bound 4. Similarly, last interval 4 to 5, upper bound is 5. And here 3, 4, 5 are the 3 different upper bounds which are taken from 3 different intervals. Among these 3 elements, which is the largest upper bound, that is 5. So, 5 is the least upper bound. So, here 5 is called supremum of this entire interval. So, there is no element which is more than to that element. Then that element is known as supremum or least upper bound. Okay. Next, come to the next definition. Greatest lower bound, or simply you can say infimum. Okay. Come to the next. If m is a lower bound of an aggregate of A and a real number greater than m is not a lower bound of A. If there is a one more element which is greater than 2m, but that is not a lower bound, then we can say m is the supremum or greatest lower bound. Okay, I will read once again here. If m is a lower bound of an aggregate A and a real number greater than m is not a lower bound of A, then m is called the greatest lower bound, GLB, or we can say it is infimum of A. For example, let us take before going to take the examples, let me discuss one more definition. If m is the least upper bound and m is the greatest lower bound of an aggregate A, then m minus m is called the oscillation of the aggregate A. So, m minus m, that is LUB minus GLB, capital M minus small m, is called the oscillation of the aggregate A. Next, let us take few examples for finding the GLB and LUB. Find LUB and GLB of the set, the sequence A n equal to minus 1 whole power n by n for all n belongs to n. Whenever the problems are like this, first let me take as n equal to 1. By putting n equal to 1, n equal to 2, we have to find out what about the values, A1 value, A2 value, A3 value. From that we can find out which is the least element, which is the greatest element. First, in this examples here, A n equal to minus 1 whole power n by n for all n belongs to n. If you put n equal to 1, A1 value is minus 1 whole power 1 by 1, that is minus 1. Put n equal to 2, A2 will become minus 1 whole power 2 by 2, that is 1 by 2. Similarly, n equal to 3, minus 1 by 3, n equal to 4, plus 1 by 4. So, alternately we are getting plus minus values. So, from only negative values, I am writing only negative values, that is A1 equal to minus 1, A3 equal to minus 1 by 3, and A5, A7 like that, and so on. And what is the nature of this this series? The series values are increasing. So, minus 1, minus 1 by 3, next minus 1 by 5 like that. It is increasing. Among this, which is the greatest lower bound here? Greatest lower bound is minus 1. Similarly, from the positive values, A2 1 by 2, A4 1 by 4, A6 1 by 6. So, and so on we will get. This is the series of decreasing terms. Among this, which is the least upper bound? 1 by 2 is the least upper bound. So, we got greatest lower bound minus 1 from among all that, from A1 to up to infinity. A1 is minus 1 and the greatest lower bound is minus 1 and least upper bound is plus 1 by 2. So, minus 1 is the infimum of A and plus 1 by 2 is the supremum of A. Let us take one more example. Find least upper bound and greatest lower bound of set A n equal to 1 plus minus 1 whole power n by n for all n belongs to natural number set. In this example also, I am substituting n equal to 1, then what about A1 value? Put n equal to 2, then what about A2 value? Like that I am finding certain values by substituting n equal to 1, 2, 3, 4 like that. If you put n equal to 1, A1 equal to 0. If you put n equal to 2, A2 equal to 3 by 2. Put n equal to 3 in that given set, value A3 will become 2 by 3. Put n equal to 4. Similarly, A4 equal to 5 by 4. After putting n equal to 5, A5 is 4 by 5. Among all this, 0 is the least element, that is 0 is the minimum element from entire that values. So this 0 is the infimum, or we can say greatest lower bound. Similarly, among all values 3/2, that is 3/2 value is 1.5. So this 1.5 is the maximum number from entire values. So we can say this is supremum of A, or simply we can call least upper bound. Okay. So for this example, greatest lower bound is 0 and least upper bound is 3/2. So infimum is 0, supremum is 3/2. Let us take one more example. After completing this example, I will move the next topic. Find LUB and GLB of an equal to minus of n plus 1 by n for all n belongs to n. Put n equal to 1 again. Here a1 equal to minus 2, put n equal to 2, a2 equal to 3/2, and put n equal to 3, a3 4/3, and a4 5/4, a5 6/5, and so on. So totally we got the elements are minus 2, 3/4, 4/3, 5/4, 6/5, and so on. It is increasing, therefore greatest lower bound is minus 2. But here limit as n tends to infinity a n equal to minus 1 minus of 1 by n, it is minus 1. But this minus 1 is does not belong to that set. Of course, this is the least upper bound of aggregate A. Okay. These are the few examples on GLB and LUB, that is infimum and supremum. Now let me discuss open sets and closed sets in real number system. Okay. And before going to start these open sets and closed sets on real number system, let me discuss few general properties on real number system. Let A comma B are any two real number systems, then mod of A minus B is known as distance of the 2 points. The distance between 2 points, mod of A minus B is always equal to mod of B minus A, means what is the distance from A to B, that denoted by mod of A minus B. Based on these mod properties, we can discuss three conditions. Based on these conditions, we can move the next closed sets, open sets, different definitions. Okay. First come to the first property, mod of A minus B equal to 0. It means A equal to B. It means the distance from one point to same that point, it is always 0. That is first condition. Mod of A minus B equal to 0. It means A equal to B. That is if and only if A equal to B. Second condition, mod of A minus B is always equal to mod of B minus A. This is known as symmetric property. The distance from A to B is always equal to distance from B to A. This is known as symmetric property. Next, this third property is most important, that is triangular inequality. Based on this third property, we have certain problems also. Let me discuss first what is the meaning of triangular property. Modulus of A minus C is always less than or equal to modulus of A minus B plus modulus of B minus C. This is triangular property. Here whatever the elements we are taking, that A, B, C are always belongs to real number system. Next, these are the notations for how to indicate the open intervals, closed intervals, left closed, right open, left closed intervals. Next, come to the definition. Yes, this is epsilon neighborhood definition. Based on this epsilon neighborhood definition, we can move interior point. Next, based on interior point, we can move open set. Based on open set, we can move closed sets. So these are the interrelated definitions. So if you know the concept of epsilon neighborhood, then we can able to know the interior points. If you know the knowledge on interior points, then we can move the open sets. Then afterwards, complement of open sets will become closed sets, like that. Okay, these are the interrelated definitions. So first I will discuss the what is the epsilon neighborhood definition. If A belongs to R and epsilon greater than 0, here epsilon means a smallest positive quantity. Almost it is 0, but it is not exactly 0, 0.0001 something like that. So that's why I am saying it is epsilon greater than 0 is a real number. Then the set x is such that x belongs to R. Mod of x minus a less than epsilon is called as mod of x minus a less than epsilon is called epsilon neighborhood of A. And it is easy to see epsilon neighborhood of real number system of a point of A, the open interval A minus epsilon comma A plus epsilon. So instead of writing modulus of x minus a less than epsilon, simply you can write it is A minus epsilon to A plus epsilon within open intervals. And the notation of this is denoted by n epsilon of a or n of epsilon comma a. This is a notation. And for example, if I say 2 is the point, and for these 2 points I am writing the open interval 2 minus 1 by 4 comma 2 plus 1 by 4. Here 1 by 4 is the neighborhood of 1 by 4 neighborhood of 2. So here 1 by 4 neighborhood of 2 this is. Next definition, let A contained R and A belongs to A if there exists a real number epsilon greater than 0 is such that epsilon neighborhood of A is contained in A, then the point A is called interior point. So epsilon neighborhood of A is contained again in A set, then we can say that point A is called interior point. If A subset of R and if for every A belongs to A is an interior point of A, then A is called open subset of A. So what is the open set definition? First, epsilon neighborhood. Epsilon neighborhood of A is contained again A, then we can say that is A is the interior point. If A contained or if and every A belongs to A is an interior point of A, as I will read once again here, I will read once again this line. If A contained R and if every A belongs to A is an interior point of A, then we can say A is a open set in R. For examples, every open interval is always open set. Why? Because for every x belongs to A comma B, there exists delta greater than 0 is such that open interval of x minus delta comma x plus delta is always subset to R. Similarly, every non-empty set and every real number system or and non-empty set, these two are always open sets. And next, last one more, next definition, and closed sets. I will move the closed sets. If A is a subset of R, then the complement of A in R, that is R minus A equal to x such that x belongs to R, but x does not belong to A, is an open in R, then A is called closed set. Okay. So the complement of open is nothing but closed set. For examples, every closed interval is always closed set, and every real number system R and every non-empty set always closed sets. So these two are the important examples for open sets and closed sets. So real number system and every empty set, these two are always open sets as well as closed sets. Why? Because the inverse of the complement of R is empty, the empty set complement is R. So one and each and every one is complement to each other. That's why I am saying R, real number system, and empty set, both are examples for open sets as well as closed sets. And finally, I can conclude with one theorem, that is the intersection of any two open sets is an open set. The union of any collection of open sets is again a open set. There are some major statements. And the union of two closed sets is a closed set. The intersection of any collection of closed sets is again a closed sets. And this is a limit point definition. And I will read just this point, then I will stop the class. Okay. A point A belongs to R is called a limit point of aggregate A if every neighborhood of A contains a point A other than A itself. This is a limit point definition, and based on the limit point, okay, the Bolzano-Versus theorem, every bounded infinite aggregate has a limit point. With this, we finished these real number system and completeness axioms. Thank you.